Okay, in this video, I'm going to talk about the basics of quantum mechanics. So we're going to go over the time-independent Schrodinger equation, the wave function, and the normalization of the probability density. So let's get started with the Schrodinger equation. Okay, like I've said before, this is the time-independent version of the Schrodinger equation. As you can see, it only depends on the wave function, largely depends, or the wave function only depends on position and not time. If you were to have the independent, time dependent form, you would have a multivariable wave function that also utilizes time as a variable as well. So, let's take a look at this wave function. So off the bat, we can see some, I guess, familiar terms. So you can, so with this one, you can clearly see that this is about the potential energy. This is the total energy, or related to the total energy. And it may not look like it, but this represents the kinetic energy. So you can kind of see how the conservation of energy kind of gives way to the derivation of the Schrodinger equation. Now, overall, the Schrodinger equation describes how a particle behaves. Okay. Moving on, let's talk about the elephant in the room, which is this, the wave function. Now, the wave function can take on a myriad of forms depending on your quantum system and its constraints. So let me give you an example. You can have this or this. So yeah, these are two different wave functions for two different systems. So, however, so despite the fact that they um, don't look anything alike, they do share similarities. One is that they satisfy the Schrodinger equation. So if you were to plug the wave function and its derivative into the differential equation, you can see that both sides will equate. Second, they're also normalizable. I'll explain more of that later. So here are the similarities. So satisfies the equation and normalizable. Okay, let's talk about the meaning of the wave function. So generally, the output of phi, the wave function, can be difficult to interpret. Now, why is that? Well, if you look at this version of the wave function, there's a big hint why. As you can see, sometimes the wave function can contain complex terms. And as a result, it can be hard to correlate it to a real physical meaning. Like, such that I, if you're confused what I is just simply the square root of -1. So yeah, this is an imaginary number, and it's hard to correlate that to physical reality. So, with this being said, what's the point of the wave function, you may ask? Well, it turns out if you multiply the wave function by its complex conjugate, you'll get a function that outputs real values which have a meaning to it. This function here is the probability density. Now, how do we know it outputs real values? Well, you take the complex conjugate and multiply it by its you take the wave function multiplied by its complex conjugate, you'll get rid of the imaginary values. Similarly, if your wave function looks something like this, where it doesn't have any imaginary values or any like complex values like I, you can just simply use the wave function. So you can just square the wave function, and you'll also get the probability density. So for this one, you would use if there was, your wave function is complex, you would use this one if your wave function is real. Okay. Moving on. Let me make some space. Okay. So why is the probability density important? Well, as the name implies, it gives you a probability of finding a particle in a given region. So, for example, say you have, say you have a box, right? Say you have a box, and you have some particle within the box. If I were to ask you, what is the probability of finding the particle within that box, which can be interpreted as a bit of a stupid question, or you could, it's obvious you would say it's 100%. How would you represent that? It's like this. So the integral of that, of finding, or the probability of finding that particle within that box is 1, which is 100%. So what does this, let's take this step by step. This is essentially summing up all the possibilities of finding the particle in a given region of the box. So, this is very important. This is very important because it allows for us to solve for certain constants. So for instance, we had the wave function earlier that was this. if we were to find the probability density, it would look like this. Oh, this is, I went too far. Ignore the 2 here. Okay, so yeah, this is the probability density. As you can see, we can now solve for A, which is very useful. This is our unknown constant. Now, why is this useful? Now that we have A, which in this case is a 2 over L, we're able to find the probability of any region within the box. So if you were to, like, you know, try to find the probability of, you know, locating the particle in, you know, half the box, that would simply be, you'll probably calculate something to 0.5, 50%. And that makes conceptual sense. You're essentially only looking at half the box, so you're going to get half, so there's only half the chance that you're going to find the actual particle. So normalization, to review, is very important because 1, you find constants, and 2, you can find all other probabilities. So yeah, these are the main reasons. So you can, and as a result of finding the constants, you can basically complete the wave function, which for us is this. Okay. Okay, the wave function is really useful now that we have it because we can solve for other things. Like, most specifically, energy. I should not have erased the Schrodinger equation. Let me write it back again. So you have the Schrodinger equation. So yeah, if you were to input phi into here, it'll get you a step closer to solving for the total energy of the system. Now, for the potential energy, for most circumstances, this is 0. So if you're dealing with a particle trapped inside an infinite square well, or a particle trapped like within a ring, you can basically take the potential energy as 0 in our region of interest.